This is the second part of the turbulence modeling history on turbulence modeling in computer age. With the advent of the computers in 1960s and the development of numerical method, it was possible for researchers to test the turbulence models for different flows. These activities were reflected in two landmark events: the 1968 Stanford Conference on Boundary Layers, the 1972 NASA NANI Conference on Fleischer's flows, for which the test calculations with various models were compared. In the same period, there were activities on the improvement of the turbulence model. More information can be found in the reference tool. For instance, the Sibich-Smith zero equation model in 1967. In 1970, Selfman formulated an k-omega model that would prove superior to the Kolmogorov model, and this model has been inherited and further developed by Wilcox and many others for many years. Now, k-omega model become one of the most popular turbulence models. Davidov in 1961 and Haro Nakayama in 1968 further developed k-epsilon model, and the significant activities in Imperial College for improving, defining, and tuning the k-epsilon model. C. Jones and Ronda in 1972 and Ronda and Sharma in 1974. And in the same period, it has been recognized that the limit of the conventional turbulence model. So, to avoid the introduction of additional differential equations, such as in the Reynolds-stress models, the nonlinear extensions has been added to Bushnitsky's hypothesis for incompressible flow. If you want to see the details, you can find the information in Namely 1970 and Selfman 1976. Powerful computers were made the implementation and validations of the proposed turbulence models possible, and thus provided the opportunities for tuning and enhancing the turbulence models. It should be noted that there are hundreds of different turbulence models in literature. Here, only some of the most popular turbulence models are presented, including k-epsilon model. First k-epsilon model was formulated in late 1960s when the computers were available. The transportation for both k and epsilon were directly derived from the Reynolds averaged Navier-Stokes equation. The model has gained a widespread use since Jones and Ronda in 1972. In 1974, Ronda and Sharma retuned the model's closure coefficient so to create the standard k-epsilon model, and made the k-epsilon model the most popular turbulence model. Now, enhanced models were available, including the normalization group RNG and the realizable models, and many other variants. K-omega model. The first k-omega model was proposed by Kolmogorov in 1942 and independently by Selfman in 1970. Spalding at Imperial College improved the Kolmogorov k-omega model in earlier 1970s. Wilcox kept improving the Selfman's k-omega model since 1970s and made the k-omega model among the most popular turbulence models. In 1994, Mentor presented SST k-omega model. The idea behind this model is to merge the Wilcox k-omega model, which is good for modeling the near-wall region, and the k-omega model, which is good for the free stream in the out part of the boundary layer, and with the newly revised definition of the eddy viscosity. This model performs very well in wide application when compared to many other turbulence models. There is a special one-equation model, the SA turbulence model, which was proposed by Spalart and Omeras in 1992. This one-equation model directly solves a transport equation for a viscosity-like variable. This model is specially designed for aerospace application involving wall-bounded flows. It has shown to give good results for boundary layers subjected to the adverse pressure gradient, but it might not be good for other types of the flows. This turbulence model was the first turbulence model applied in the hybrid lens LES model in the detached eddy simulation DES in 1997. Reynolds-stress model RSM, or sometimes called the 7-equation model. This is a turbulence model which abandons the Bushnitsky's hypothesis of isotropic flow by solving all components of the turbulence transport directly. Therefore, it has advantages of handling the anisotropic flows, for which the other turbulence model based on the Bushnitsky's hypothesis might fail. These specific flows include the flow with sudden change in mean strain rate, the flow over covered surface, the flow in ducts with second motions, the flow in rotating flows, and in some three-dimensional flows, and more. Soon after the boom of various turbulence models, the research activities in this field slowed and shifted to large eddy simulation LES, and specifically later to the use of hybrid lens LES method, mainly due to the difficulties of the lens modeling for the complicated flows, such as the flow separations, as well as the much increased computer powers. It is well known that in LES, large energy-carrying eddies would be resolved numerically, and only the small eddies are modeled. Generally, these small eddies would be much more isotropic. Thus, it is easier to be modeled, at least in principle. The first LES model was proposed by Smagolinsky for atmospheric research in 1963, and the first engineering application happens in 1970s. At the late 1970s, a research group at Stanford University took the lead in the development and the application of LES. However, LES applies a severe demand on computations well beyond the general practical applications. The mesh requirement in LES is proportional to the power of 1.8 to 2 point of the Reynolds number. For example, for a car or an aeroplane, the LES mesh would be 10 power of 11.5, and the time steps would be 10 power of 6.7. Thus, pure LES modeling are still limited in the simple flows of low Reynolds number, and many as research tools for providing some detailed information for the turbulent flows. To ease the great demand in LES, Spanard and co-author in 1997 proposed a hybrid length LES model named as the DES model, and it soon becomes a very popular approach in the research community. The DES model is with very practical requirement on computation. The mesh is 10 power of 8 and time steps 10 power of 4 for a car or an airplane. The original DES was proposed as the boundary layer is treated by length and the regions of massive separations are treated with LES. Now, different hybrid length LES models have been developed and are being used, including the ambiguous zonal and non-zonal hybrid length LES model and the relevant changing issue. Strictly speaking, all hybrid length LES models would be zonal method, but in the research community, the zonal length LES is defined as in the simulation, the zones must be predefined for length and LES, while in the simulation, if the length and the LES models are triggered using certain criteria, it is called as the seamless model, as the DES model above. However, we might have some tricks for applying hybrid length and the LES model. LES could have same or very similar mathematical equations as those in length. Thus, the numerical implementation would be same or even easier than the length models. However, it should be noted that the conventional LES on a 2 coarse grade of wall-bounded flows, especially in attached flows region, can be very anomalous and would be inferior to even simple conventional lengths. During the history of the turbulent modeling, there are some famous and interesting predictions. In this slide, I will introduce some of these unsuccessful predictions. The first one is, can computers would replace wind tunnels? In 1975, Chapman and his co-author claimed computers would begin to supplement wind tunnels in the aerodynamic design and test process. Since the huge successes in the turbulence modeling were made in that period. However, this has not happened even after 45 years, and probably it might never happen. Kraft in 2010 extensively discussed how computers and internal testing can be integrated together to reduce the overall cycle time for development of an aeronautical system, rather than the computers replacing wind tunnels. The second prediction is, can RANs survive LES? In 2005, Handrich believed RANs will further play an important role, and the increase in the computer power would be used more to utilize the advanced Reynolds models to shorten the design and the marketing cycle. In 2009, Sparnat predicted a form of a lens-LES hybrid that is capable of 4 lens functions in boundary layer will be used in the foreseeable future in many industries. In 2017, Brody predicted the pure wall-resolving LES is not practical because of too much demand for computer power, while the employment of either LES with wall functions or hybrid LES lens model would be the choice. In 2018, Durbin gave a review, and the statement is, the demise of lens closure has not happened because the expenses in computer time, man-hour, and the requirement for high-resolution grading will make the extensive use of LES unfeasible. The third prediction is, when LES and DNS will be available for practical applications. In 2000, Sparnat predicted that the LES and DNS would be ready for practical applications in around 2045 and 2080 respectively. However, after 16 years later, Sparnat and his co-author revised the claim and stated, by now, we are not confident of this for the 21st century, or even that it will ever happen. Turbulence modeling is a very hot topic in research, but there are many challenges involved in this. We have the common issue in CFD modeling, such as mesh generation, numerical algorithms, robustness and automation, data management, etc. But in here, the specific challenges in turbulence modeling will be introduced. For lens modeling, the challenges would be for fluid translation and separation, the modeling for off-design conditions, for instance, the aircraft takeoff or landing, rather than the cruising condition, the development and the improvement of advanced turbulence models, and the selection of correct turbulence models. For instance, in ANSYS Fluent 18, there are 8 different turbulence models, and in OpenFOAM version 6, there are 18 turbulence models plus 18 turbulence models of low Reynolds number. For LES and DNS, the computational demand too high, expensive for practical application. For LES, the mesh is proportional to power of 1.822 point of Reynolds number. So for a car or an airplane, the mesh for LES is 10 power of 11.5, and the time step is 10 power of 6.7. For DNS, the mesh is proportional to the power of 9 divided by 4 of Reynolds number, plus the time step. It would make proportional to Reynolds number cubic. Same for a car and an airplane. DNS mesh would be 10 power of 16, and the time steps 10 power of 7.7. So the example for the large-scale modeling for an opening channel for a friction Reynolds number RE tau equals 5,200. In the modeling, the mesh in x direction is 10,240, in y direction 1,536, and in z direction 7,680. So it made the grid roughly 120 times 10 power of 9. So this modeling has been done on a petaflops computer Mira. It ran several months to finish the modeling. The very hot topic is the hybrid lens LES. This approach is being enhanced in academic research and on the road to industry applications. The hybrid lens and the LES mesh requirement would be 10 power of 8. Time step would be 10 power of 4. However, we have some challenging issues. The first one is the issues in both zonal and non-zonal hybrid approach need to be adjusted, and the turbulence in the attached boundary layer need to be resolved with more confidence.